quick recapitulation of what we have seen in the last class. We have seen the design and the flow characteristics in a heat exchanger. The heat exchangers that we have seen can be the simplest possible form of a heat exchanger would be a double pipe concentric heat exchanger, in which the liquid will, one liquid will flow through the tube, the other will flow through the annular space. The more common and slightly complicated design comes with shell and tube heat exchanger. So there would be one shell and multiple number of tubes which are connected to a tube sheet, and the flow is going to the flow of one liquid is going to be through those tubes, and they will come from the other side, and on the shell side the liquid is going to be at cross flow over the surface of the tubes. So the flow of the tube is going to be straight, whereas the flow in the shell side is going to be tortuous. It's going to be made tortuous purposefully so as to enhance turbulence and to increase the heat transfer coefficient. And we have also seen that there can be multiple tube passes and multiple shell passes. So 1 2 heat exchangers, 1 shell, 2 tube, 2 shell, 4 tube passes are quite common. The purpose of using multiple passes is to ensure that the residence time is more, residence time for a specific fluid is going to be more inside the heat exchanger, allowing better heat transfer such that the exit temperature, the overall heat transfer efficiency, overall heat, the quantity of heat transfer between the cold and the hot fluid can be increased if we increase the residence time. So that's why we have multiple passes present in some of the heat exchangers. But any increase in number of passes will also enhance the pressure drop, and pressure drop plays a very critical role in deciding about whether to use multiple passes, what kind of should be the diameter of the pipe, and so on. So these pressure drop and the enhanced heat transfer these two should be balanced with the overall cost of heat transfer, keeping in mind the overall cost of heat transfer. So increase in heat transfer by increasing turbulence would result in an increase in pressure drop. So that's obvious. So there has to be a balance between the two. This we have discussed. Furthermore, we have also seen that depending on the direction of flow, the flow of the hot and the cold fluid may be parallel or may be counter flow. So we have parallel flow heat exchangers and counter flow heat exchangers. In some of the cases, part of the flow is going to be parallel, whereas part of the flow is going to be counter. So we will have situations where mixed flow also prevail. So depending on the direction of flow, it can be parallel, counter, and mixed flow. So this is something which we have shown. And so we talked about parallel flow, counter flow, cross flow, and concentric tube, which is the simplest form of heat exchange equipment. The basic constructions, we spoke about shell and tube. As I said, number of passes, the baffles which are obstruction to the flow path and which makes the fluid move in a zigzag pattern in a tortuous path inside the shell with the idea of increasing the heat transfer coefficient. The tubes are connected by a tube sheet, and the tube sheets, the heat exchanger is closed by different types of heads, and the design of those heads, design of the tube sheet, baffles, and so on, they essentially complete our understanding of the heat exchange equipment, their efficiency, their performance, and so on. And as I said, pressure drop plays a critical role in deciding all these factors. So that's the basic configuration of a shell and tube heat exchanger, which is most common and which we are going to see in next. The other part that I spent some time on is about fouling. With prolonged use, in between maintenance, there's going to be some deposition or some reaction, corrosion between the liquid that is flowing and the inside of the tube surface or the outside of the tube surface, which is exposed to the shell side fluid. The formation of these scales, the fouling phenomenon essentially increases the heat transfer resistance, because they add some resistance to heat transfer from, let's say, the cold fluid to the hot fluid, cold fluid inside the tube to the hot fluid outside of the tube. So if I did not have any resistance, any fouling, then there would be three resistances in series. One is the convective heat transfer coefficient for the inside of the tube, convective heat transfer coefficient for the outside of the tube, and the thermal resistance of the tube material, which also would depend on the thickness. If we have fouling, which is the realistic situation, then two more resistances are to be added to these three resistances. One is due to the fouling inside of the tube, and the other is fouling due to fouling on the outside of the tube. So the overall heat transfer coefficient, generally denoted by capital U, is a sum of all these resistances. The first resistance, 1 by U, U is some sort of an overall heat transfer coefficient. So inverse of that is the resistance to heat transfer. So 1 by U should be the sum of all these 5 resistances in series. So in engineering design, it's important to know what is the overall heat transfer coefficient of a system, of a pipe shell assembly, in order to ascertain what is going to be the length of the heat exchanger required to consider to affect a specific amount of heat transfer between the hot and the cold fluid. So this overall heat transfer coefficient is very important, and most of the design equations or design exercise of the thermal design exercise of heat exchange calculations end up with finding out what is the value of the heat transfer coefficient. Everything else will follow from there. So I'm going to show you the relation, as I explained to you, how to connect overall heat transfer coefficient with HI, the convective heat transfer resistance based on the inside, HO, the conduction resistance, and the two fouling resistances. So if you look over here, this 1 by UA, that's this U is the overall heat transfer coefficient, which is, you can define it based on either based on inside area AI, where AI is pi DIL, or you can do it, you can express it in terms of an external area, where AO is simply pi DOL. So these two are the inside surface area of the tube and outside surface area of the tube. So this is so U can be defined based on the inside, or U can be defined based on the outside. So the suffix of A in this term would determine how do you express U, in terms of internal area or in terms of external surface area of the tube. The first one is the convective resistance, this is the conductive resistance, and this is the convective resistance on the outside. Whereas RF double prime I is the contact resistance for the inside surface. This is the contact resistance for the outside surface, and this RF is known as the fouling factor. So the values of the fouling factor are known for different types of fluids, and they would definitely depend on the time for which this heat transfer equipment is in use and so on. But the knowledge of this RF for a specific fluid is essential in order to find out the overall heat transfer coefficient. At many instances, the heat transfer, the significant part of the heat transfer resistance comes from the contact resistance. So what I am going to do now is to show you some of the typical values of the heat transfer coefficient that you would expect in real systems. So some of the values of U, which would give you some idea of U that are generally encountered. This U is in watt, SI unit, watt per meter square Kelvin. So from water to water, the value is about 850 to 1700 watt per meter square. This water to oil is slightly lesser. The important one here is steam condensing on the outside of the tube while water is inside the tube. This is an important value, which is about 1000 to 6000. So, look at this number. This is the largest of the three that I have shown so far. So, whenever steam condenses, let us say I have a tube through which water is flowing, and the steam at a certain temperature, and pressure is, if it is saturated steam and it at a certain pressure, it's condensing on the outside. So, when it does, the temperature of this surface is going to be constant. Not only the temperature of the surface is going to be constant, which would correlate to the pressure of the saturated steam that you have, it's also this is also going to maintain a constant temperature and a very high value of heat transfer coefficient. So, the value of heat transfer coefficient is significantly larger than the others, and therefore, you have the steam condensing is going to give you a high value of heat transfer coefficient. So, the other one is finned tube heat exchanger, which is maybe water in tubes and air on the outside, air in cross flow. So, if for that case, it's going to be only 25 to 50. So, as you can see, whenever you have a gas, you are going to have heat transfer from a liquid to a gas, or in any process which involves heat transfer to gas, the value of the heat transfer coefficient is going to be significantly smaller than that between liquid to liquid. So, between liquid to liquid, water to oil or water to water is 500 to 1000, whereas for finned tube heat exchangers, where the tubes itself will have fins like this, the one that you see in the radiator of a car, the heat transfer coefficient is only 25 to 50. Compare that as the natural convection, it's going to be of the order of 10 only. So, this is going to be of the order of 10. So, looking at the different values of the heat transfer coefficient, you then have some idea that you would always like to have a situation with a high value of heat transfer coefficient, but you are not that lucky all the time. So, you may have to use natural convection. You will encounter natural convection in many of the applications, and whenever you have from water to air, the heat transfer to a gas, use of fins may be justified, but even with the use of fins, you would get only from 25 to 50 watt per meter square Kelvin, significantly lower than that of that when two liquids are interacting thermally and exchanging heat in between. So, this is just a rough idea of the values of U, that the values of the overall heat transfer coefficient that you generally encounter in real systems. So, now let us look at how to think about or work on how to calculate the overall heat transfer coefficient. And in order to find out the overall heat transfer coefficient, we first have to define how to define a temperature difference, because when you think of a tube, the heat that enters, the liquid that enters at a certain temperature and the liquid that goes out at a certain temperature, the total amount of heat gained, let us say its gain, heat gain is simply going to be m dot Cp T at the inlet minus, rather T at the outlet minus T at the inlet. So, mCp delta T. Similarly, the liquid which is flowing outside of the tube with a different mass flow rate, it is also going to gain or lose some heat, and mCp delta T would give you the value, the amount of heat that the outside fluid transfers to the inside fluid. However, this is based on overall energy balance of each of the streams separately. But these two streams are also interacting thermally across the tube wall, where it faces 3 resistances or 5 resistances, including the thermal resistance, as we have discussed before. So the amount of heat that gets transferred is simply going to be Q is equal to U, where U is the overall heat transfer coefficient, times delta T. So m dot Cp delta T for the inlet fluid is equal to, due to energy balance, m dot Cp delta T for the outlet fluid, and this total heat exchange can also be expressed in terms of an UA delta T. U is the overall heat transfer coefficient, A is the surface area, and delta T is some sort of a temperature difference. So in order to find out the sensible heat change, mCp delta T, we know precisely what delta T is. It's T inlet or T outlet minus T inlet. But what am I going to write for the delta T, which is associated with the overall heat transfer coefficient, or U? Is this delta, because this delta T, as you can understand, is going to vary with position. So as you move in a specific direction, the value of delta T would be different at different points, and whether you have parallel flow or you have counter flow, the value and the behavior of the change of delta T with position would also be different. So a judicious choice for delta T has to be evaluated in order to use the equation that mCp delta T of one fluid is equal to mCp delta T of the second fluid is equal to UA delta T, what that delta T is going to be. So that's what we are going to find out in our next exercise. So in order to do that, so we are first going to start, as I have mentioned, with an enthalpy balance. The enthalpy balance would simply give me Q as m dot for the hot fluid IHI minus IHO is equal to m dot cold fluid IC at the outlet minus IC at the inlet, where this is the fluid enthalpy and I is for the inlet, so this is for the outlet, and this I is for the inlet. So in other words, you can express it as m dot Cp of the m dot H Cph Thi minus Tho equals m dot Cp of the cold fluid Tco minus Tci. Okay. So these temperatures, the temperatures that I had used here are mean fluid temperatures. All temperatures are mean fluid temperatures at a given location. It's not a point value, it's just the area average value. And I also know, as I have explained to you, Q is equal to UA delta Tm. So this delta Tm is the temperature difference. What kind of temperature difference I do not know as yet between the hot and the cold fluid. So this I am going to do it for parallel flow heat exchanger and for counter flow heat exchanger. So let's first start with parallel flow heat exchanger. So for parallel flow, the profile would look something like this. This is the X and this is T. So this is THI, temperature of the hot fluid at the outlet, temperature of the cold fluid at the inlet, temperature of the cold fluid at the outlet. So this is the temperature difference at the inlet, and this is the temperature difference at the outlet. and if I take a small slice, so here the temperature difference, let's call it this as delta T, and some amount of heat is going to come from the hot fluid to the cold fluid as in the direction that is shown, and this difference is the dTc, change in temperature of the cold fluid, and this is dTh, change in temperature of the hot fluid as we move in this direction. So over this infinitesimal length, the temperature of the cold fluid increases and the temperature of the hot fluid decreases. So this dq for this we can write as minus m dot h Cph dTh, so which is some sort of a capacity dTh. So since the energy is reducing, so that's why I have put it minus sign here, and for the cold fluid it's going to be m dot c Cpc dTc, which is defined as Cc, capacity of the cold fluid, time dTc. And these equations you can simply integrate to obtain the total heat which is over the entire length of the heat exchanger as m dot c Cpc, temperature of the cold fluid at the outlet minus temperature of the cold fluid at the inlet. And similarly you can write it in terms of the hot fluid also, in which case it's going to be m dot h Cph, temperature at the inlet minus temperature at the outlet. Additionally, you also have dq to be u delta T yet to be determined times dA. This is the amount of heat that comes from the hot fluid to the cold fluid. So this delta T at this point is Th minus Tc, the temperature of the hot fluid minus temperature of the cold fluid, and from this I can simply write d delta T is dTh minus dTc, since delta T is Th minus Tc. So d delta T can be written as 1 by Ch plus 1 by Cc. So dTh comes from here, dTc comes from here, so it's simply dq by Ch, and here it's dq by Cc. So this is what you are going to get for d delta T, and dq can also be written as u delta T times dA from this relation, and 1 by Ch plus 1 by Cc. So I bring this delta T over here, and therefore I have d delta T by delta T is equal to minus u, the heat transfer coefficient, Ch plus Cc. All these are constant and therefore they can be kept outside of the integration sign. So this is at location 1, which is my location 1, and this is my location 2, 1 to 2, and between 1 to 2. So that's a simple expression which can be obtained, and once you integrate this with the locational values incorporated in there, what you are going to get is simply ln delta T2 by delta T1 is minus u times A Thi minus Tho by Q plus Tco minus Tci by Q. All these derivations are there in your textbook, and therefore you are going to get is minus Ua by Q Thi minus Tci minus Th at the outlet minus Tc of the outlet. For parallel flow, delta T1, if you look at delta T1, this delta T1 is simply Thi minus Tci, and delta T2 is Tho minus Tco. So for parallel flow, delta T1 is Thi minus Tci, and delta T2 is THO minus TCO. So, therefore, Q is UA delta T2 minus delta T1 by ln delta T2 by delta T1, where this term is simply the log mean temperature difference. So, the final form of this equation is going to be UA delta T Lm. So, what I see here is that the overall heat transfer coefficient is related to the total transfer of energy. This is the surface area, and the delta T, relevant delta T to be used is not the arithmetic mean or any other mean. The equation simply tells you that you have to use the logarithmic mean temperature difference, delta T2, which is this, delta T1, which is at the inlet, and ln delta T2 by delta T1. However, the value of, if I simply look at delta T2 by delta T1 and find out what is delta T arithmetic divided by delta T log mean, what you see is when it is 1, obviously there is no difference. When it is 1.2, this is 1.0028, but when it is 1.5, it starts to affect your results, and with increase in this ratio of delta T2 by delta T1, the delta T arithmetic, the departure of delta T arithmetic from delta T Lm starts to become significant. So, as long as the ratio of delta T2 by delta T1, this ratio is within 1.5, it really does not matter if you are using an arithmetic mean or a log mean. But for any change in temperature ratio delta T2 by delta T1 beyond 1.5, it is always advisable to use the log mean temperature difference rather than simple arithmetic temperature difference between the inlet and the outlet. So, the heat transfer relations are to be calculated based on log mean temperature difference, not the simple temperature difference, the arithmetic mean of the simple temperature difference. So, this we have done for the case of parallel flow. Now, let us look at how it is going to behave for the case of counter flow. So, we are looking at counter flow now, and in counter flow what you see is, so this is for counter flow. In counter flow, your temperature, hot temperature is going to be, this is TH at the inlet and this is TH at the outlet, and in the case of and let us say this is TC at the inlet and this is TC at the outlet. The direction of flow is counter flow. So, the hot fluid flows in this direction, the cold fluid flows in the reverse direction. So, what you have over here is delta T1, this is location 1, this is location 2, and this is delta T2. Delta T2 is simply THO minus TCI, and as before we again take a small slice of this heat exchanger where the change in the hot side temperature is dTH and the cold side temperature is simply dTC, and the heat flows in this direction is dQ. Note that in the case of counter flow heat exchanger, the outlet temperature of the cold fluid can exceed the outlet temperature of the hot fluid, which was not possible for the case of parallel flow. So, that is a specific advantage characteristics of counter flow. So, here also as before you can write in the same way that the total amount of heat transfer is simply going to be UA delta T Lm, but in this case delta T1 is simply going to be THI, delta T or THI minus TCO, whereas delta T2 would be THO minus TCI. And as I told you before, for the case of the counterflow is going to be more efficient than the parallel flow when the temperatures and the flow rates are kept unchanged. Just one more, there are few special cases that one needs mention here is the case when three cases. You remember that CH, the CC and so on. The CH is simply defined as Cp times delta T, and CC is CPC CHC delta TH, and delta T as I have shown before. So this C are simply the heat capacity rates. Which are nothing but m dot Cph, m dot Hcph, m dot Ccpc. So C is the heat capacity rates, which is the product of mass flow rate multiplied by heat capacity. So when you look at the heat capacity rates, it's simply mass flow rate of the hot fluid times Cp of the hot fluid and so on. So some of these special cases, three of these special cases that we would examine here is, the first case is CH. The capacity of the hot fluid is very large as compared to the capacity of the cold fluid. So in this case, these are all temperature as a function of x, location 1 at the inlet, location 2 at the outlet, and this is how the temperature profile would look like. So this is when the temperature change. So this is for the cold fluid and this is for the hot fluid, and the hot fluid temperature does not change at all when CH is very large as compared to CC. So this, in this case, this straight line is when CH tends to infinity. That means for, let's say, for a condensing vapor. So for a condensing vapor, the temperature, as I mentioned before, will remain constant, which for a condensing vapor the CH will tend to infinity. So the reverse is when you have the CC is very large, CC is very large as compared to CH. So this is the hot fluid, this is the cold fluid, and this specific situation will arise when it's going to be a straight line, will arise when you have an evaporating liquid. So for a evaporating liquid, as long as it is evaporating, its temperature is going to remain constant, and this is how it would look like. And for the special case where CC is going to be equal to CH, both these lines, parallel flow, in counterflow, this you would see that delta T1 is equal to delta T2. So therefore, everywhere in the flow path between the hot and the cold fluid, the delta T will remain constant. So the takeaway from this is for both for parallel flow and for counterflow, this Q can be expressed as UA delta T, whereas the special cases where the capacity CH is much more than CC, which is the case for condensing vapors, there is almost no change in temperature on the hot side of the fluid, which is obviously going to depend on what's the temperature and pressure of the gas which is condensing, of the steam, let's say steam which is condensing. On the other hand, if your Cc, the capacity of the cold fluid, is much more than that of the hot fluid, then therefore you are not going to experience any change in the cold side temperature. And for the special case, when the same fluid is flowing inside and outside of the tubes, the Cc and Ch are same, so the difference between the cold fluid and the hot fluid temperature at any given location is constant. So whatever you have at the temperature difference you have at the inlet will be the temperature difference at the outlet and any point in between. So this is what, so we now know the basic fundamentals of what temperature difference to be used and what kind of behavior we will have depending on the capacity of the fluid in parallel flow and in counter flow. But not all flows are purely parallel or purely counter flow. There are mixed flows as well. So in the next class we will quickly take a look at the mixed flow cases.